Hi everyone, I'm Alex MacDiardmid and I do the content marketing here at Submer. I'm here with our Director of R&D, Mark Miyoshi, and the lovely Forced Convection Heat Sink package. So Mark, when did this project begin and what was your motivation behind starting this project?
So we started this project about a year ago. As for the motivation, basically for the last 7-8 years, we've been using 1U, just standard off-the-shelf air heat sinks in immersion. And that was okay for a long time, but with the rising TDPs, it was no longer an option. So we had to figure out how to better cool CPUs, and that's why we started this project. What came out of that initially was this, what you see here. It's what we call an immersion optimized heatsink, and it features thicker fins and wider fin spacing, or a fin pitch, as some people call it. These work well, but I would say the improvement over this is marginal, maybe. You're looking at maybe a 5C improvement at 350 watts. So to take to the next level so that we could cool next generation CPUs that could be in the 500 watt range, we needed something else. And that's how we got to this. This is the forced convection heat sink, as you mentioned. What we're doing here is we're confining the flow from fans or propellers. They're propellers, but in this case, they're fans acting as propellers. The flow of this is confined to the dimensions of the heat sink. So the flow from this has to go through the fins. That's not the case with the forced convection heat sink. With the forced convection heat sink, or this heat sink, as a matter of fact, you can increase the flow as much as you want down here, but it'll just go right around. And as a result, the CPU temperature remains unaffected. But with this, the flow here has to go through the heatsink, and that's how you get much better cooling, and that's how we're able to get to this kind of power level.
So which CPU is featured here?
So this is a special workstation platform by Intel. Mm-hmm. The CPU here is a W93495X. As you may observe, it's at 800 watts, which is way more than a standard server would do. A standard server currently tops out at about 350 watts for Intel. This is a special workstation, and we're overclocking the heck out of it, and that's how we're able to get to this. And well, not just that, but because we have this cooling unit on it, we're able to get to 820, 830 watts.
So we can see the watts being cooled here. What else can I see on the screen?
This is the average junction temperature. So it's the temperature of the silicon underneath.
So I feel like we have a lot to cover with the technology. Starting from here, what can I see here?
Yeah, so this is part of the voltage regulator set. So you got the voltage regulators split to here and here. And these are the chokes right above, and then below you see these copper heat sinks. These are copper heat sinks that were put over the MOSFETs. Again, part of the voltage regulator module. I didn't need to put these copper heat sinks on there. I just put them on just to kind of as like an aesthetic thing and just to be safe. When I got this board, it initially came with huge heat sinks that were like this by this. So this whole portion was covered, and it was like that tall up here too. I took it off, saved a ton of space, and I ran it with no copper heat sinks like this, and it worked just fine. So that just kind of shows you the advantage of immersion. You don't need huge heat sinks where normally you would.
And so here I can see the DIMMs. Mm-hmm. What are the benefits of using immersion cooling specifically for DIMMs?
So with DIMMs, immersion cooling is perfect because it represents a lot of heat because you've got a lot of DIMMs, right? But the heat is kind of evenly spread out, and it's not really concentrated in one area. For example, if you take a server with 48 DIMMs and each one is doing 20, 30 watts, that's a ton of heat, but it's spread out over a wide area, and you've got these nice channels, so you don't need a heatsink, as opposed to a CPU or a GPU where you've got a ton of heat concentrated in a relatively small area. So in immersion, it's perfect. With air, it can be difficult. You need a lot of air to cool that kind of heat. And with with DLC, they do have full coverage DLC systems with copper jackets that cover each DIMM, and those work just fine. But when you've got 48 or 36 DIMMs in a server, that can be expensive and cumbersome, I would say.
Are there any other ways that you can compare this with direct-to-chip cooling?
I would say the components are certainly a lot cheaper. You don't need the tubing, you don't need brazed copper, you don't need pressure testing, any of that stuff. It's just a heat sink with propellers on it. The propellers would be powered by the board. You just plug it straight into the motherboard header. It works. When the CPU doesn't need cooling, it will just not, the fans won't turn on. So it self-regulates that way, in terms of power.
Nice. Can you tell me a little bit about what we can't see, what's going on behind the scenes here and in the back?
You're talking about the internals?
Yeah.
Yeah, so you're probably wondering why this box is so big. There's a radiator at the bottom here, and we've got fans here. So what's going on is there's fans here in the back, pushing fan air out this way, and there's pumps here. What's going on is the fluid gets pumped up into here, back, I guess, up here, forward, and then up through here. And then once it passes this here, it goes back down to the radiators where it gets cooled, and then the cycle continues. And the fans are pushing air out this way, so that means the cool air gets sucked under here and gets rejected out that way. And
in this section here specifically, what's happening in the back?
So, yeah, I put this here basically because this is a special workstation platform that actually requires two fairly large ATX power supplies, and that means you've got two 24-pin MOBO headers. So there's a ton of cabling, and that's with PCIe and CPU 8-pin connectors. So there's all sorts of cabling here. So I had to basically cover that because without that, it would just look terrible. And to do that, I just came up with this kind of design so that it would kind of look nice. And we got the Submer logo here, and that's that.
And what would happen if one of these fans were to fail, for example?
Oh, great question. So I've gotten that question a lot over for the past month or two. So yeah, the fans, well, I'll start off by saying that I've got two of these fans in my lab. They've been running for, like 7 months now straight, 24/7, no problems. So I don't think reliability is going to be an issue. But anything can happen, of course. So should the fans go out, I will show you what happens. I'm going to turn off one of the fans. I turned off this one. So now it's going on one fan. So it was going at 820, 830, something like that. And now it's going to go down because it no longer has the same amount of cooling. And the CPU has to adjust the power level because it doesn't want the CPU to overheat. So the power level is going to go down, and it should go down to about 780-ish. It looks like it's leveling off at 780, yeah, which is still really, really good, going off of one fan, right? And yeah, so I think it's pretty much leveled off. So 790 even, that's one fan. Really good, right?
Pretty impressive, yeah.
So that's one fan. Now I'll show you what happens when both fans cut out. Now both fans are cut, and now it's going on pure natural convection. And this is pretty cool because you can kind of see the heat coming off of here, the plumes. What's surprising here is, and this really surprised us when we were testing this, is that the holes here don't really provide much restriction. So the performance of the natural convection of this heatsink really isn't affected very much. It's affected very little. So it still works really well, as you can see, because it's still going at 580, and I think it'll go down about 5, maybe 60, something like that once it levels off. So yeah, it's still working great. Just means that with the solution, your CPU will never die. Even if the fans go out, it'll work just fine, even for next generation CPUs.
So I think we've covered more or less how it works. Correct me if I'm wrong, Mark. Are there any benefits aside from this being able to cool next generation chips?
Yes. So even for current generation chips, because of the thermal resistance offered by this solution, you can run much hotter temperatures. That means it could mean heat reuse. It could mean you downsize your cooling infrastructure in your data center, less water usage. So all these things, you save money, CapEx, OpEx, all that stuff.
Nice. And do you have any next steps planned for this project specifically?
Yeah. So we're actually going to test just what I just mentioned. We're going to put a server with these units in one of our tanks to get actual test data on how hot we can get the inlet and the outlet temperatures. And we should have that data pretty soon. So that should be pretty interesting.
Nice.
Yeah.
So I guess you guys will have to stay tuned on our social media channels and on submer.com to catch what's next for this project. Thank you so much, Mark. See you next time.
Submer, data centers that make sense.